This video is about Joule heating and will empirically prove the maximum power theory. Okay, imagine a long cardboard tube filled with touching marbles. Push one end and the other marble drops out the other end almost instantly. But it's not instant, as the energy you impart into that first marble slightly deforms its neighbour, and then its neighbour's neighbour is deformed. This deformation you can only see at a microscopic level, but it's in fact like a super fast energy impulse, because these touchings, these deformations move through the marbles at such a fast speed it looks instantaneous. To our eyes anyway. It's extremely fast though. If we had a completely stiff, rigid set of marbles all touching that could not be deformed easily, the speed will then be much closer to an instantaneous event. Electrons through wires can be thought of in this same way. The only major difference is that battery now does the pushing, although the energy impulse for electrons in copper is close to the speed of light now, because electrons are very rigid. Even though individual electrons will move very slowly, so they're only moving from one little step to the next, very, very slowly, but the impulse is super fast. In this lab I've set up a circuit of a battery, a source resistance RS and a load resistance RL. This diagram shows the copper wire packed with electrons. Here you can see all the electrons through this wire. Okay, these electrons are huge in reality. There are billions and billions of electrons in here, but I just wanted to give the idea of they're all touching and everything's very tight within this this wire, so everything's very, very close to each other. So of course as you move one electron, all of them will move, and it's very similar to the marble idea. So this diagram shows the copper wire packed with electrons. For all intents and purposes, these are like the touching marbles. When we connect up battery, the charge electrons will flow around this circuit continuously at a rate that's dependent on the energy of the battery and how much obstruction to charge flow that there is. If there is a little obstruction at the load resistance, so if this is a very small obstruction, then only a small amount of battery energy will be used by this load resistance, because only a small amount of energy will be required to get the charges through RL. And if the obstruction is so large that hardly any charge can flow, so if it's very, very restricted, then RL will again use only a very small of energy, because there's not enough charge going through, so very small energy is used again. So this lab will show that there is a halfway point between these two extremes, where the load resistance RL will use its maximum energy from the battery, and we'll find it is when the load resistance equals the source resistance. So here's the diagram, just going over those points I've just made. Here's the circuit, and it says here for maximum power the load resistance RL must equal the source resistance RS. Now the lab will show that this is true. You can show this mathematically, but I don't want to do that. I want to show it empirically so we can actually have actual measurements of what's going on. The rate of charge flow is always fixed at the moment the battery is connected. Its rate will then not change. So what I'm saying there, that this charge flow has a speed, and it's fixed at the very moment we switch the battery on. It's not going to change. The resistance here will determine that speed on switch on, yeah? So if you've got a large resistance, you know, a very narrow space, a very narrow squeeze here, then the charge that will flow, which is a steady flow, will be a fixed value for that, and it will be a very small value. If this resistor doesn't show much squeeze at all, it's very wide, then more charge will flow, and it will be the same flow, and that flow will be fixed as soon as we flick the battery on, as soon as we switch it on. And the marble example here, I've just shown how, given an example of how electron flow is. We've got a very large tube here, I've actually extended it so it's right round the Earth, 24,000 miles. When we push A here, B will move at the instant we push A. Well, it seems like it's the instant, but it's not really. But this is how fast an impulse of energy can move, and that's really what electricity is. It's a very fast movement of energy. Electrons themselves move very, very slowly. That's the important thing. And the force of pushing electrons through small obstructions, this causes thermal heat, and we can measure that heat. Okay, here's a very quick sketch of the breadboard setup of the lab that we're going to do in a minute. We have here 10 resistors ranging from 1 ohm up to 22 kiloohms. We only be testing one of these at any one time. For convenience, they are all in the breadboard, and I'll use a wire to ground to select each one in turn. So this wire here, I'm going to select each one of these resistors in turn and take my measurements and then tabulate those measurements. For each resistor tested, the temperature probe, so I'm going to use a temperature probe here. I'm going to connect a temperature probe to each resistor, which is a really good proxy of heat. So when we measure the temperature and when we plot it out, we will know that the temperature variation will be directly proportional to the actual heat. Yeah. So that's a very good way of doing an empirical experiment to show energy released through the resistors. When we switch on a circuit, a period will elapse long enough to take a temperature reading. All three values, the voltage with the voltmeter, current with the ammeter, and temperature with the temperature probe, are tabulated in a simple table. So you can see I've got the voltmeter, got the ammeter, temperature probe. Here is the circuit. I'll show you what we've got here. So the circuit here on the right, we've got the voltage there, the voltage battery there, and we've got the source resistance. Here we've put the ammeter in line with the source resistance and the load resistance, and across the load resistance we're measuring the voltage, yeah? And then we're going to tabulate all these values for all these different resistors. So we're going to have the voltage across the load tabulated, the current going through the circuit, which will be the same all the way around the circuit. The current is always fixed. And then the power is simply the voltage times the current, because that's joules per coulomb, and current is coulombs per second. So if you multiply those together, you're going to get joules per second, yeah, which is power, yeah. So that's very quick Ohm's law. So this is the power column here, and then the interesting one is the temperature. So we're actually physically measuring the temperature with a temperature probe across the resistor there. So what we expect to see is when we plot these values out, they're scaled on the same graph. We do expect to see a very strong correlation between these two curves. They should look very, very similar. If they don't, then something's gone wrong with the experiment, because it's well known that the power across the resistor here is equal to the heat that's released. Yeah, so the energy is basically converted directly into thermal energy across the resistors. So then we'll just move on to the experiment and see what happens.